Greetings, all faithful ME 273 students. This is your honorable professor coming to you technologically. I hope this finds you well and prospering. The goal of this short video, well, I hope it's short, is to further clarify and point out some things that I'm looking for in these reports that I'm having you do. Please remember the purpose of these reports associated with these guided activities is to have you practice and learn how to produce a good written description of a problem or problems that you've solved. This is of utmost importance for your engineering education, and please try to fight the urge to think of my comments and my pointing out things that need to be improved in these reports. Please fight the urge to think of this as, I don't know, being nitpicking or wanting to make you jump through a hoop. I promise, and I swear upon my solemn honor that that's not my purpose in doing this. My purpose is to make you into a good engineer, and if you take my advice and take it to heart, then you're going to prosper not only in our class, but in the long run, all right? Also, I want to allay some of your fears. I know you're probably a little concerned because I'm starting to hand out evaluations for the revisions of that first guided activity, and so far there's quite a few not passes on that revision. All right, so let's take a peek. This is what I want to do in this video. Just show you an example. This is a revision of guided activity number 1. Remember, that's the falling sphere. This is a revision that was done by one of your fellow student teams, and I've got the names blocked out and the memo part of the report blocked out in black here, so you don't know who it is. If the authors decide to reveal themselves to anybody, that's up to them. All right, so let's go through this, and I want to go through my comments and my highlighted parts of the report and just give you some insight into what I'm looking for and give you some hints or maybe some tips on ways that you can improve things. All right, so you'll notice my judgment here is for the revision number 1. That's the first revision after handing it in. I still have a not pass for this one, and I'm going to take you through and show you why. And what you're going to see, though, is that this is a pretty decent report now. It's not yet quite very good. It's good. We're shooting for really good to excellent is what we're after, all right? And I'm going to try as hard as I can to make you do it and to learn this. So you'll notice I have here, it says a few minor revisions yet needed. All right, so let's take a look. Here's the objective section. Remember, that's the first part of these memo reports. All right, so let me move this little comment box, and let's read through what your fellow students have here. It's not too bad of an objective. In particular, I want to point out the highlighted text here. The Euler method predicts the next value of a function, in our case the position and velocity functions, at a very small time later than the starting point at time t. We start off with an exact acceleration equation, then multiply previous acceleration values by delta t, which gives us our velocity equation. The same thing is done for position, but velocity is multiplied by dt or delta t instead. There's several things that's not too bad of a prose description of the Euler method, but why describe equations when you can just put the equations in? And if somebody, remember who your audience is. This is of utmost importance. You remember who your audience is. Your audience is students at your same level of preparation, but who are not in our class. And so they have no idea, or maybe they've heard of the Euler method, but they certainly haven't seen it any time recently. So they don't really know what that is, and you're describing equations that would be that should be displayed. That would really be the way to do it, to make it clear what you're describing here. All right, now let me move these things a little further out of the way and just try to take an objective look at what's presented here. Let me see if I can't move these out of the way further here, and then I'll put them back. Look, the Euler method is described in words. Why use words again? Equations are what we're after. Then you go through, and by the way, time steps, this for a fellow student would be really confusing to see a dt here. That sure looks to me like an infinitesimally small dt. There's no reason why you can't use delta t here, because it's really a finite delta t we're describing. All right? Then you go through the bowling ball to be able to measure how accurate the dt is. You're not really measuring how accurate the dt is. I mean, just be careful what you write. Right? An exact solution must be known for position and velocity. These solutions were met by solving the acceleration differential equation. The equation for acceleration was derived. This might look like Newton's law to somebody, of course. Try to look objectively like I'm looking at this if I were a student in your shoes, not in our class. I have no idea what G is. Do you know what G is? What is R? What is this? Because I'm familiar with Newton's second law, I probably know what sigma F equals ma is. Got that, but then you say integrate, and look at all this stuff. Do you know what those letters stand for? So this can be improved, as I say here. Equations should be numbered and referred to in the text. Make fonts consistent. By the way, we're mixing something with Comic Sans here. Different fonts and sizes are distracting, but these should be labeled. Certainly all the parameters labeled here. D, rho, A, M, G. I have no idea what these are. As well as put in the numerical approach. Put the equations in. That's really what's going to pack the punch for showing somebody what you're up to. It's a good description, but the equations need to be included, right? So again, to sort of summarize this, you don't have to write a book on this. I mean, it doesn't. The improvements I'm describing are just a couple minutes of added detail here. Describe what all these parameters are. Give a little more than just, describe what G and R. You have to tell your reader what they're looking at. Number the equations. Include the equations for the numerical approach, number them also, and then the description can refer to the numbered equations, all right? And furthermore, don't use dt, use delta t. Go ahead and call it what it is. dt is just the short little thing we use in our computer code because we don't want to have to go grab a delta. All right, I hope, overall, I think one of the big messages to try to convey to you students is take pride in this. Right? You're not just describing this so that you're satisfying me so I can give you a good grade. Look critically at this. Does this describe to you something that a fellow student would even be able to follow? You already lost your reader here. They have no idea what D is. D plays such an important role in this whole thing, by the way, that it's really good to point out what it is and where it comes from. Again, you don't have to write a book, but you have to have some detail which describes what all these ridiculous letters are. Otherwise, this is just a bunch of stuff. I'm lost already. All right, so that's the first section. Needs improvement. Now, let's look at the results section. All right. Exercise 1. This is a pretty good graph. It's labeled. It's clear that I'm looking at a falling bowling ball. Position versus time, and you can see the dynamic range of the graph is nicely used. Everything's labeled. The units show up. So I know exactly what I'm looking at here. All right. Now, one thing that is missing, though, if I'm going to look at this, especially in the context of defining in the previous section exactly what all these are, when I get down to the graph, I want to know what the parameters were that generated this. And so I've suggested to many of you, you could either somehow label the parameters right on the graph itself or maybe in a caption. And by caption I mean a small little piece of text that is somehow neatly attached right under the graph that is also separate from the main text, all right? It's a little bit of a formatting thing, but you have to have the parameters. Again, if you define everything properly here, one thing your reader's going to be looking at is not only the result, but they want to know what parameters did you use to generate this. Not only out of curiosity, but especially if I want to try to reproduce this, I need to know what parameters were used, d, rho, a, m, as well as dt, initial velocity, and all those different things that we built into our control panel. Right? You should really indicate those close to the graph. And that's what I say down here in this little square here that says parameters should be included here. You're making your reader do too much work to find them. By the way, what I mean by that, it says, as seen in our appendices, look at the highlighted text, as seen in our appendices, the parameters that generated this plot were the bowling ball specifications in the control panel, as well as the Euler position function. You're pointing them to the appendix, and as I say here, you're making your reader do too much work. If I've got to scroll, here, watch this, if I've got to scroll all the way down to the appendix here, and then find out let's see, what parameters did you use? Okay, and by the way, you might actually, when you show one of your scripts in the appendix here, you might show some generic parameters which for another graph above might not be the same parameters that generated the graph. All right, so already I've had to scroll down here, look at these parameters. Now in order to, okay, that's what you, but wait, what did that look like? Now look, I got to go all the way back up and find where I was at. Okay, is that where I was at? Well, no, here's where I hope this demonstrates the simplicity of facilitating your reader's effort by pasting those parameters right here somewhere, either in the caption or right on the graph. All right. Yes, they show up in the appendices also, but the appendix plays a little different role. That's for someone to look at your code and to study the code itself, not to connect the graphical results with the actual physical parameters used. All right. Now, same thing here. I don't know what the parameters are, although it's a very nice graph, right? So this is a very good looking graph, and should be what was expected. I have a little box here. Notice I've highlighted this, and once again, I don't want to be seen as, I mean, you know, as a professor, as a teacher, I could evaluate your stuff, and I can find little nitpicky things to make you fail anywhere, and I'm not trying to do that. But when I read this, let's just read this objectively with me here. It says the ball, I'm starting right here, all right? The ball accelerates until it hits a terminal velocity, and then falls with constant speed until it hits the ground. As before, dt of 0.001 was used in our Euler computation just because it was simple and led to a neat curve. Notice I said define neat. I really don't know what you're talking about here. Our Euler computation, so you're trying to make the point that as before, this value of delta t was used because it was simple. What is simple about this number? It's small. Is it that it's smaller than the value used? Simple and led to a neat curve? Honestly, I'm not trying to be weird about this, but I don't know. I've seen neater curves than that. Is that what you're talking about? So, especially in science and engineering, you have to define your terms. Neat may very well have some meaning here. I don't know what it is because you haven't defined it. All right? Probably you need a little better wording there, because I don't think probably neat is the best thing to do. But again, if you define it then and it makes sense, then by all means use the word neat. Here I really have no idea what's being described in that sentence. That sentence alone, by the way, wouldn't be enough for me to say just go back and revise the whole thing. I might, if that were the only thing wrong here, I might just make the comment as suggestions for improvement and maybe pass it anyway. But I hope you realize there's more than just that here that I'm suggesting a revision on. All right, let's see. Going down, they included. By the way, this is always okay. This was not necessarily asked for, but the acceleration was included, which is kind of nice, actually. I can kind of see what's happening here. At time 0, we start with a pure free fall. There's our good old friend 9.8 right up here. And you can see that as it goes down, it does indeed asymptotically approach 0, which means that the resistive force, or the drag force, is now around 27 seconds. Excuse me, somewhere in there is approaching the actual weight of the thing, so there's no more acceleration. Here's another room for improvement comment about the wording. Here the graph of the acceleration of the bowling ball, the respective time is shown. Normally, acceleration is seen as just a straight line. Again, I don't know what you mean by normally here, and my comment is normally air resistance is acting, right? So normally it wouldn't be a straight line. Even if you drop something in the lab, in the simple mechanics laboratory from your intro physics class, you don't ever measure 9.8 exactly. So again, I wouldn't make you do the whole thing over just because of this word normally, but you really have to be aware of what you're describing. This just doesn't make sense. The reader sees this normally, acceleration is 9.8. Well, not really. 9.8 is an extreme idealization where we've neglected air resistance. All right. So be aware of what you're writing. There's probably some more examples of this coming. All right, exercise 2. Now here's where, remember, in this exercise 2, the goal is to try to determine accuracy, and the way we increase the accuracy of our numerical solutions is to lower dt, or our delta t. Once again, I'm going to try to urge you, get in the habit of using actual delta t here. For your reader, if you're using dt, that looks like an infinitesimally small thing, and it can be confusing, even though we all know what we're talking about. Right, so this is actually pretty well done. This is a very nice graph. The legend is clear. I can actually see which is the estimated or the computational solution, which one is the exact we're comparing to, and you can see what delta t was when that generated the curve. Again, I'd like to see the other parameters nearby, but this is pretty good. Now, and then on the next graph, we're going from comparing exact and delta t equals 1 to exact and delta t equals 0.1. Now, these look very good. The descriptions are all very good. I can see exactly what's happening, and I wouldn't fault this. However, I personally think that it really is best to put all of these, if you put not only these pairs, but put exact delta t of 1 as before, and the delta t equals 0.1 all on the same graph, and then you can see the trend. You actually observe that multiple curves are converging here. It's a little bit a matter of taste. I think it looks better if you put them all on one. That way you can just have one graph that tells the story. You have a legend that describes all the curves on there, and you don't have multiple graphs you have to describe and refer to. This works. It's not bad the way it is. It's just a suggestion. Put everything on the same graph, and it becomes really, really well done, I think. Let's see. Here's notice this. They zoomed in here, and this is a beautiful graph. You can see it zoomed in, and I think they described what they were doing here, decreasing. Maybe, let's see. It says, as seen here. Oops, I wanted to move that. Move it. As seen here, it's much more visible that there's a clear difference between the two models, even with dt set to 1. The difference between the two values is that this may not seem entirely bad, but for our purposes, we want it to be within that accuracy because it is less noticeable. Here's another one of these very vague sentences. Because it is less, there's two things I want to point out. Because it is less noticeable, because what is less noticeable? Look at my comment here. Is less noticeable the criterion for your accuracy? If so, you must define what noticeable means in the context of the graph scale. This is not a little, it's very confusing for your reader who, again, doesn't know what you're doing here and what the purpose of this comparison is. We want it to be within 0.01 meters per second accuracy because it's less noticeable. Is that your criterion? If so, it's a really vague criterion that doesn't do much for your reader. How can your reader take this and apply it to anything? The principle is, I want to be within 0.01, and there's some mysterious less noticeable aspect to this. You really have to define what you mean, but more importantly, why did you choose 0.01 as your accuracy criterion? Now, you don't have to justify it necessarily, but you really have to indicate why you think 0.01 meters per second accuracy is important. In other words, why is it important to be within 0.01? Is it a certain percentage difference in the solution compared to the exact? Is it related to some measurement you think you could make that would produce the same accuracy? I hope I'm making sense here that, this isn't bad. It's just you haven't communicated, one, what the nature of the comparison is, two, what your criterion for determining accuracy is. Right? So that should be updated. And again, you don't have to write a book. This is maybe 2 sentences will clarify all the things I just described. Let's go on. Here's the comparison. What is this? This is the smaller delta t. Again, if you put them all in, that's what this comment says. Again, if you put them all on the same graph, it's much more effective, I believe. Although, this is not bad. You would pass just doing this if there weren't those other issues at play here. All right. Here's another zoom in. Okay. And then accuracy of position versus time. A lot of the same issues apply here. I don't know what parameters were used to generate these. It's a very nicely labeled graph, but I don't know the other parameters. Probably it's more effective you put them all in the same graph. And then just make sure you define your accuracy criterion that you use to determine when you actually have a delta t which is small enough. There's another very nice zooming in, right? So these are good graphs. And to take this from a not pass, from this point to a pass, is just a little bit more work. Important work, though. All right, what's this here? It says, finally, let me see what I say here. Finally, we saw that delta t equals 0.0 when we were able to get an Euler solution we were comfortable with, right? For a position. Again, why were you comfortable with it? For velocity, we wanted our Euler and exact solutions to be within that of each other because velocity is something harder to measure and keep. Here's another one of these mysterious sentences. It sounds like you're going to really enlighten me on something. We wanted our Euler and exact solutions to be within 0.01 of each other because, and then it just sort of flops here. Velocity is something harder to measure and keep precise? What? Harder to measure than what? And keep precise? Isn't that what you're trying to do, is keep it precise? So that's my comment here. Harder to measure than what? What is the criterion? It looked like you were going to tell me what it was, but then we went to this mysterious harder to measure and keep. I just have no idea what you're describing there. All right, that should be improved. In number 4, now remember, for part 4, exercise 4 and 5, you found the delta t, which gives you an accurate solution, and now you study how the model behaves. This is very good. This is beautiful, actually. And so I put a very positive comment here. This is a good graph. It's very clear what you're getting from the graph. Everything's labeled. Oops. The units are nice. And look, this was included in the graph, the x and y coordinates right here, which tells me at 440, and it's consistent with the description down here, that at 440 meters, that's where the ground is, as described here, and you hit the ground at 10.6. Beautiful. I can look at this graph, and I almost don't even have to read the rest of it, because it's obvious that you're dropping a bowling ball 440 meters, and it took 10.64 seconds to get it. It would be very nice, though, once again, to see what parameters you used. Okay? I mean, what if I'm interested in the specific value of the drag coefficient? It's a major effort for me to have to search and figure out what that was that generated this plot. I think, and there's the velocity for that same one. And then exercise 5 here, this team chose to drop a golf ball. And again, very well done. I can see exactly a golf ball should take 16.3 seconds. So this part's very well done. And it's not that much effort to take this and make it a very nice report. Finally, look at the conclusion. Now this really does not have to be a book, and it shouldn't be. All right, and what I mean by that, you don't have to write a lot. But here's the conclusion, and let me just read this because I thought this was a very good conclusion. Based on our results, we can conclude that the Euler method is only accurate as we make it. That's true. That's the absolute truth, and that's what you get out of this exercise. By changing the value of the change in time, you should maybe just put delta t there. It's a little bit bulky, right? Changing the value of the change in time. Changing the value of delta t would read much better. We were able to provide more accurate data. We noticed that when we suggest a smaller value of delta t again, the discrepancies between the values also decreases. Therefore, we can conclude that the best accuracy when computing the Euler method is significantly small delta t. However, we take close enough look, we can see that a discrepancy is still. It's very well done. Very good conclusion. And then they also notice something else about another observation here. Right. So if you look back, oh, by the way, here's the appendix with all the code. The code is very nicely commented, is what I'm trying to say. I might, my only minor, and this wouldn't be enough to make you have to revise it on this alone, but make sure you put units in here. So for instance, drag coefficient should put unitless. Air density, kilograms per cubic meter. Just good to have all the units in there. And everything else looks pretty good. And you're inside the loop. Look at this. This is important. Inside the loop, you've got it indicated. By the way, again, this is minor, but it's not the Euler method for time. You're not approximating time. You're just incrementing time. You're increasing it by delta t every time step, right? But they do have the Euler method for position and the velocity very nicely labeled here. And the acceleration equations. I can look at this and I know exactly what every part of this program's doing here. Here's the plotting, comparison of the two methods, right? So overall, this is very well done. Yet I'm going to, as I said, oops, let's go back up. I'm still giving this a not pass. And one more admonishment to fight the urge to think that I'm just being a jerky prof. All right, I don't do that, and I don't want to give the impression of being a jerky prof by making you go and add this stuff. But the hope is if you take this to heart, take my suggestions, try to learn from them, then maybe in the next one, or certainly by that GA number 3, you're going to be producing such beautiful reports. Who knows? I might even just start throwing out points to everybody. All right? So that's the goal. Have the right attitude, and as usual, give yourself enough time to work on this. I mean, of course, if you are scrambling 1 hour before this thing's due and you're trying to put together a nice report, it's not going to happen. All right? You know that, and I don't have any real wisdom for you other than get to this stuff as soon as you can. Don't put it off. I know you're busy. I know that you have other classes and other things that you've got to focus on, but with those, it's the same advice. You got to do it, and so you've got to give yourself enough time. You've got to allow yourself time to do well. And it's only if you're giving yourself time to think these things through and to take my advice and apply it that you're actually going to do very well. All right? So please direct any questions or concerns via email to me. And I shall see you all soon. For now, it's On Prof signing off.